The broadcast is now starting. All attendees are in listen-only mode.
Good day, everyone. Thank you for attending our Design Verification and Analysis Tools in TracePro webinar. I'm Andrew Knight, Technical Sales Manager here, and I have with me Dave Jacobson, who is our Senior Applications Engineer, and he will be presenting today. The format of the webinar will be an overview of the various tools available in TracePro for analyzing and qualifying the performance of optical systems. This will last approximately 20 to 30 minutes, and the presentation will be followed by a question and answer session. You can ask questions at any point during the presentation using the question window on the GoToMeeting control panel, and we will address all questions afterwards. So with that, I will turn the meeting over to David, and thank you again for attending.
Thank you, Andy. Again, my name is Dave Jacobson, Senior Applications Engineer here at Lambda Research. As mentioned, today's topic is going to be on the design verification and analysis tools in TracePro. And as Andy just mentioned, at any point if you have questions, please feel free to send them in using the questions box in the GoToWebinar control panel, and we'll take a look at all your questions at the end of the webinar. Before we get started, I just wanted to remind everybody about the current releases of TracePro and Oslo. TracePro is now at release 7.0.3 and Oslo is at 6.5.2, and these are available for download from our website for users with current maintenance and support agreements. And if you're not up to the current release, we always strongly suggest that you update to the newest version. So, in this webinar, we're going to take a look at some of the design, verification, and analysis tools available in TracePro. We're going to try to show you how to apply some of these tools to your designs, and hopefully give you an understanding of how these tools can help in your design and verification process. We'll also take a look at how you could use some of these analysis tools to check the tolerances of your designs, and then we'll wrap up with a question and answer session at the end. So basically, we'll start off is, what is design verification analysis? In basic form, it's checking to see if your design meets the desired goals. Some examples of some design goals. Well, they could be a Flux, Irradiance, or a Luminance target, so how much light you're getting onto a target. It could be a beam pattern, a specific angular distribution that you're looking for. It could be color, if you're doing color mixing, multicolor LEDs, or if you're looking for specific color coordinates, or CCT, correlated color temperature. Could also be looking for uniformity, how even is the light across your surface. Could be a luminous or radiant intensity target. Could be a radiance or luminance target, so light being emitted from a surface or from a source. Could also be an efficiency goal. You're designing an luminaire and you want 85% efficiency on your target. You can use these tools to check that. So, what are some of the design and verification analysis tools available in TracePro? And these are all accessible from the analysis menu in TracePro. If you go to analysis, it'll bring up all the options here. And we're going to look at some of the key ones here. We're not going to touch all of these in today's webinar, but the ones we'll look at will be the Irradiance and illuminance maps, the Candela plots, the luminance and radiance maps, the flux report, the incident ray table, and the ray histories. And we're going to go through these one by one as we go along here today. So first, we're going to look at the Irradiance and illuminance map. Now, what is an Irradiance and illuminance map? Well, the Irradiance and illuminance map displays spatial distribution of incident or absorbed light on a selected surface. It'll show you flux or flux per unit area. If you're looking at an Irradiance map, you're going to be looking at the radiometric units. So you're going to see watts, watts per meter squared, or watts per foot squared. If you're looking at the illuminance map, you're going to be looking at photometric units, units of visible light. So these would be lumens or lux, lux being lumens per meter squared, or foot candles. Foot candles is lumens per foot squared. And the units can be changed by going to Ray Trace Options, and Analysis Units in TracePro. You can also look at uniformity with the Irradiance map, efficiency, relief plots, profiles of the spatial distribution, contour plots, CIE color coordinates are available, and these you can get both X, Y, and U prime, V prime color coordinates. You can get the correlated color temperature, the CCT, and there's also a true color mode, so you can see and get a feel for what the light would actually look like to a viewer's eye. As we go through this webinar today, I'm going to use this as my example for a lot of these analysis tools. And this is a simple little LED spotlight. I had made this model a couple of years ago. It has 7 LEDs, and it has, let me just turn on my pen here, and it has a lenslet array here of 7 lenses in front of each LED. And the LEDs have a white LED property for the spectral distribution. Here's the actual model we'll look at. In this case, I've inserted a target surface here. And this is just a block that I inserted into TracePro, and I'll look at the light hitting the front surface of this block from this LED spotlight. So here's an example of an irradiance or an illuminance map. In this case, if you notice, I have my units set to lumens, so I'm in the photometric range. So I have lux for my scale here. As I mentioned, that's lumens per square meter. If we look down here at the display, we can see the total flux on this surface. We can see the incident rays, the number of incident rays hitting the surface. We can see the minimum, the maximum, and the average lux values. So in this case, we have an average lux value of about 970 lux. And we can see the distribution of the light on this surface. Most of the light's in this circular pattern. If we look at our scale over here, it's a little bit brighter here in the center. And we can also see we have some bits of stray light here out on the side. And if I actually had this on a larger target surface, that stray light would actually form a ring around this whole object. We'll take a look at this bit of stray light here a little bit further along in this webinar, and take a look at how we can look at where that's coming from and what you can do about it. So in the Irradiance map, we can take a look at the way it actually looks in several ways. There's a lot of color options available. In this case, we have 2 different color gamuts that we're using, one with red being the brightest, and then in this one here, blue and white are the highest irradiance. And we also have a grayscale option. And these can also be done on a white background or a black background. And a lot of times this is just user preference. How do you make the map look the way you want it to look? And I should mention, all of these options are available by selecting the Irradiance Illuminance map options when you're in the Irradiance or Illuminance map in TracePro. Just do a right click and you can bring up the options menu like that. So the Irradiance map is made up of a series of pixels, and these are defined in that Irradiance Illuminance options. The default setting is 50, so the map is 50 pixels by 50 pixels. And if we look at this image here, we can actually see the small square pixels of the map. If we change that to a higher resolution, we could say go to 100 by 100 pixels, and we can see the pixels are smaller. We'll see more detail on the map, but the map's also a little noisier. So as you increase the number of pixels, you're going to want to trace more rays to make this to be a smoother, less noisy image. And each one of these pixels basically collects rays or collects flux and then reports at the end of the ray trace how much flux has hit each pixel. There's a smoothing option available. So here we see the irradiance map, unsmoothed and smoothed, and this will just smooth the values from pixel to pixel. This can make a cleaner looking picture, but it can also mask some detail. So really what you want to do is trace enough rays at a high enough resolution without smoothing to get a good image for your irradiance map. The smoothing will affect the readings you get slightly. I mean, here we see a total flux of about 980 lumens. Here it's about 983, and then the max and min values will change slightly because this will report what's actually on this map after it's been smoothed. So just be aware that you could see some slight changes if you apply smoothing, and it could smooth over some detail you're looking for. The irradiance map can also show you an efficiency value. The default setting here is it will show you flux divided by emitted flux. So it's the flux received on this target divided by the total flux emitted by your sources. In this case there was 7 LEDs, so it's the flux from all of those LEDs. And we see here we're looking at about 44% efficiency for this luminaire. There's a relief plot option for the irradiance illuminance map, and this gives you a 3D representation of that irradiance map. There's also profiles. And when you turn on profiles, it sets a crosshair in the target here, and it'll show you here to the right the profile in the horizontal and vertical axis of these crosshairs. And you can also go and move this around. If I had TracePro set up here, you could just left click and drag these crosshairs around to any point in your model, and then you'd see the profiles for that point over here on the right. You could also display the irradiance illuminance map as a contour plot. There's also the option of looking at color. In color, we have a couple options here. If we hover at any point, if we hover our mouse cursor at this point, it'll give us the CCT of that point, the correlated color temperature. In this case, it's roughly 4,300 Kelvin. And then in the status window at the bottom of TracePro, you'll see the color coordinates. In this case, we're set up for XY coordinates, CIE XY values. So we're roughly 0.37 by 0.37. There is an option in the irradiance illuminance map options to change this to U prime V prime, and you'd see the slightly different color space for that U prime V prime coordinates. As you can see, it also gives you the location here on the Planck curve inside the color space. You can also set the display to be true color. So now we'll see, I mentioned this was a white light LED, and you get a feel for what the actual color from this system would be. Could be useful if you're doing color mixing, if you have color filters in your system, and you want to see effects with and without those. Okay. Now we're going to take a look at the Candela plots, another one of the more common analysis tools in TracePro. A Candela plot will display the angular distribution of light. So really it'll give you a measure of radiant and luminance intensity. For radiometric units, it's watts per steradian. And for the photometric units, it's going to be Candela. And again, those are changeable under the Ray Trace Options menu in TracePro, where you can set your analysis units to either radiometric or photometric. You can also, in a Candela plot, you have the option of an iso-Candela or a Candela distribution for the method of plotting. I'll show you the difference of those here shortly. And you can also export IESNA or Illumdat files from the Candela plots. If you're interested in this, I would suggest you download our October 2010 webinar, which was devoted to working with IES and Illumdat files in TracePro. And that's available at www.lambdares.com/webinars. I should note that this webinar will be archived and placed in that same page here shortly after we finish. And as all of our previous webinars are also archived there. So we encourage people to take a look at that, download any webinars that may be of interest. Here's a couple Candela plots. In this case, these are Candela distributions. And you have the option of rectangular or polar, just displaying the coordinate system, different coordinate systems. And what these are is they're slices of the sphere containing the source. And if we had a source here, this would be in effect rotating a detector around a source like this, and then displaying that data here. And you can add multiple slices to this if you want. In this case, I'm showing only a single slice because my data is symmetric. But if you had an asymmetric source, you could add additional slices and see that asymmetry in angular space. If we look here at the rectangular one, we see these little bumps here out at right around 40 degrees. And those actually correspond to the bits of stray light we saw earlier in the Irradiance map. If I go back up here. Those correspond to these areas in the corners of this map. So you can see that type of information in different forms. And they are here as well, but it's kind of down in the very bottom or at the center of this curve, so it's a little more difficult to see in the polar. An isocandela plot, and again, this is available both for rectangular isocandela and polar isocandela, shows you both azimuth and polar angles in the case of the polar isocandela, or rectangular, in the case of the rectangular isocandela, horizontal and vertical angles. So this is showing you a collection of slices. So this would be light projected onto, into a hemisphere, say. Again, we see our little bits of stray light here. So these give you more complete information because you're seeing both horizontal and vertical or polar and azimuth angles. In the case of a polar graph, the Candela distribution for the polar would be a slice across this data. So how would this look if we sliced it across here or sliced it across there? So the Candela distributions represent a snapshot of the isocandela. And the isocandelas offer a little more complete information. Okay, now we'll take a look at luminance and radiance maps. The luminance and radiance maps display the luminance or radiance of a source or surface. So this could be light coming from, say, an LCD computer display, light being reflected off of a surface, light directly from a source. For radiance and luminance, the radiometric units are watts per meter squared steradian, or for photometric units, it's Candela per meter squared, foot Lambert, or millilambert. Again, switching your units in the analysis units in the ray trace options in TracePro. And there's also a true color mode in the radiance and luminance maps, which could give you a true color or a sort of like a photorealistic rendering of your source or your object. Here's how you set up a luminance or a radiance map in TracePro. You're basically defining an eye position. So this would be where your eye is or where your detector or camera is. And you define a target. In this case, it's the front of my little LED spotlight here. And then this target is divided up into pixels. And you control the number of pixels. And what a luminance or radiance ray trace does is trace rays from the eye position back through the target to the sources. And you control the number of rays that are traced through each one of those pixels. And after you run that ray trace, here's some of the results you could see. This The pixel values here were a little bit coarse. I believe they were about a 1 millimeter by 1 millimeter pixel. But here we see it set up for luminance. In this case, my units are Candela meter squared, or nits. So I'm in the photometric units. And we can also see a true color representation. So this is giving a feel for what your eye would see from this source if you looked right at it. And again, we have these rings around here. Okay, moving on now, we'll take a look at the Flux report. The Flux report shows the flux on all surfaces in a model. You can set it to display all objects, or you could also set it to display just a single or selected objects. So you can edit the Flux report down to only show the surfaces or the objects of interest. And in the Flux report, you'll see the number of rays, the incident, absorbed, and lost flux for each object, surface, source, and wavelength. So here we're looking at the receiver, which is the front surface of my target object. We can see the surface property that's applied. It's perfect absorber, the surface area. Here's all my wavelengths. In this case, from the first LED, there's 5 wavelengths. And my second LED, again, each of the 5 wavelengths. The number of rays, the incident light on this surface, as well as the absorbed light. In this case, I have my target defined as a perfect absorber, so incident is equal to absorbed. And you can also get information on lost rays. So how are rays not getting to your target? In this case, we have some of the options are they escaped the model, they fell below the flux threshold. If you expand this out here, they beyond the number of total scatters defined. There's several columns of lost data here available. Another tool in TracePro is the incident ray table. And the incident ray table displays information on each ray hitting a selected surface. It includes the flux, the XYZ spatial position, XYZ direction vectors, and this is for each ray, as well as the polarization information, if that's applicable. You can use the incident ray table to create file sources. We did a webinar back middle of last year on light sources in TracePro. And if you're interested in looking how to use the incident ray table to create a file source, I suggest you go take a look at that one as well. Another good webinar to take a look at. And the incident ray table can also be used in conjunction with display selected rays. And that's an option under the analysis menu to show each ray path graphically. So here's an example of the incident ray table. In this case, this is it right here. And we see each ray, 1, 2, 3, 4, on up to however many rays are hitting it. It'll only show it in tabular form here up to 50,000 rows. But you can export this and then open it up in Excel as well to look at it. I've selected this ray here, ray 4. We see the flux, the XYZ position, the XYZ direction vectors, and then the polarization information here. And we can as well, if we go up to analysis and then display selected rays, we'll graphically see that ray. And if you were to then arrow down through this ray file or this incident ray table, you'd see the ray changing. So you'd be able to see each and every ray one at a time. And the last tool here we're going to take a look at is ray histories. So ray history, it'll show the path of each ray through a system in tabular format. And this includes flux, XYZ position, XYZ direction vectors, as well as polarization and optical path length for each node. So here we see this is ray number 1. It starts out, it's emitted from the LED1 object. Polarization information is here to the right off the screen. But we can see its position, its flux, optical path length is 0. We then go down, it strikes the front lens, so it strikes surface 8 of the front lens, then it strikes surface 0 of the front lens, and then it arrives at the receiver. So you could track each and every ray, see what the optical path length is, see what the flux is at any point in your model for any ray. Okay, now let's take a look at using some of these tools on a model in TracePro. This model here is a ceramic-bodied xenon lamp. It has an elliptical reflector, it has a pair of electrodes inside, a glass window on the front. A lamp you may see in a high-powered projection system. In this case, I have it focused onto a rectangular light guide here, and I'm looking at the light at a target here right at the exit of the light guide, and then a little bit further out, and I want to see the differences there. Again, something similar you may see in a projection system using the square light guide to set up the shape of the beam that you want. Then we're going to look at irradiance maps here for both target 1 and target 2. And I have these targets set so they're not absorbing. So these irradiance maps are actually showing incident flux as opposed to absorbed. Now I have 2 irradiance maps open at the same time here in TracePro. Normally TracePro will only show you 1 irradiance map at a time. But what I did is if you go to each of these surfaces, open the irradiance map, and then save it as a text file, you can then go up into the Tools menu in TracePro and bring up the Irradiance Illuminance viewer, which will then allow you to browse to the file and open it up. So you can have, in this case, as many irradiance maps open as you want. These are saved irradiance maps, so they don't change as you go from surface to surface, but it would let you see the irradiance distribution on 2 different surfaces at the same time. So this is target 1, and it's right here at the exit of this light guide. And here's target 2, a little bit further out. And we can see we're starting to get a hole in the center here. So our bright pattern actually it's a little dimmer in the center, whereas right at the exit of the light guide, it's a lot more uniform. So this is something that could be good to know if you were then projecting the end of this light guide, and you may start to see a hole in your light. And if we go to the Candela distribution, we can see why that's happening. We actually have very little light in these central angles here at the center of this beam. And that's the nature of elliptical reflectors. Because you have a hole in the back here and shadowing due to the electrodes, they don't have a nice uniform angular distribution. And if we look here, this is the rectangular Candela distribution, and this is the rectangular iso Candela. We can see here a nice big hole in the center. So if we shined this or projected this end of this light guide onto a wall, we'd start to see sort of a donut-shaped beam of light as opposed to a nice uniform pattern that's filled in the center. So it's a way you can use the 2 different tools here, the irradiance map and the Candela plot, to see what's happening in your system. Okay. I'm going to go back here to my little LED spotlight to look here at another example. And I wanted to look at what was causing this ring of light, or in this case it's right here just in the corners, this stray light. And to do this, I used an option in TracePro, whereas if I'm in the irradiance map, if I hold down the Shift key and the left mouse button, I can drag a box around the area of interest. So I did that here to this box. And then you can go to Analysis and Display Selected Rays, and it'll show you just the rays hitting the irradiance map that are hitting just that area of interest. So we could then go back to our luminaire or our light source here and see where that light's coming from. And if I zoom in on my source, I can see here it's actually coming from the spaces between my lenses. So that's light that's not hitting my area of interest or my target. So what could I do to get rid of that? In this case, what I did is I applied a black paint to the surface here between my lens elements. I reran my ray trace, and those areas of stray light are gone. So we've improved our uniformity on the target. We've eliminated that bright ring around our target. So we improved the overall uniformity of our luminaire. So another way to use these tools here in TracePro to kind of do some analysis and to do some troubleshooting. Where is this stray light coming from? And then that can lead you in the direction of where you need to apply fixes to your model. And the last thing we're going to look at here is we're going to take a look at checking design tolerances using some of these analysis tools. So why would you want to check your tolerances? Well, you want to see if you actually have this part made, and obviously not every part that you get in is going to be perfect. So how much room for error is there in your design? And what you can do is you can vary the parameters of your model elements and then check the results using the analysis tools in TracePro. You can also set up a scheme macro to automate this task. So you could write a little scheme macro. It could, say, move your lamp inside of your reflector, or change your reflector shape slightly, or even change the output of an LED and see what the results are going to be. So here's a very simple model that I made. And I took a lens. There's an LED here that's acting as my source. And I varied the radius of curvature on this lens from 11 to 12 millimeters in tenth of a millimeter steps. And then I saved the irradiance map on this target surface for later analysis. And to do this, I wrote a small scheme macro here. This macro actually has a lot of extra parts in it because the original design goal here for this macro was to figure out the best uniformity, what curvature gave the best uniformity. So there's some extra steps in here. But basically what this is doing is allowing the user to input a starting and ending point in a number of steps. So I said in this case I went from 11 to 12 millimeters, and I did 11 steps. So it gave me results every tenth of a millimeter. It draws the lens using that radius. It runs the ray trace, saves the irradiance map, each map with a unique name, and then steps back through the process, changing that radius of curvature each time. As I said, in this macro here, it also would then go back and save the one that had the best uniformity. But that's extra steps not necessarily needed for just checking, say, for radius of curvature changes. Here's the results. I pulled up those saved irradiance maps, and here we go from 11 millimeters to 12 millimeters. You see the changes in the irradiance map. And I actually just took and graphed the total flux. That's all I was looking for in this case. I normalized it to the peak value. So I see my highest value here is at 11.8 millimeters on the radius of curvature, and falling off in either direction. So if this was a design, if this was a lens I was using in a design and I wanted to see the effect of the fact I may not always get an exact radius of curvature, what would that do to my design? So with that, we're going to wrap up the webinar for today. And we can start to take a look at any questions and answers. And I'll have Andy come back on here. If we can.
I'm back.
Okay, excellent. And I see we do have some questions, so.
We do indeed.
Yeah.
So let's see what the first one is. It looks like relative to Candela plots, can I customize the angular resolution displayed on the charts every 5 degrees or 10 degrees or whatever, for example?
You can set the number of points being displayed in the Candela options. So you can use that to control the number of, basically the the angular resolution is controlled by the number of points. Let me see. Let me go back here. We'll just go into TracePro here for a second. And here I just did a right click in the Candela plot. And if in this case I have a Candela distribution, this plot points here will control the angular resolution. So if I set this to 10, we can see we have a much coarser resolution. So yes, you can control it that way. Okay, next question.
Next one looks to be, is there a link to download your macro?
Not at this point. I can see about getting that put up on the website. It would be in the, once I get it up there, it will be in the, under the TracePro technical support, examples, and then macros. I will see about getting that put up in the next day or so.
Great.
Okay.
Another question relative to Candela distribution plots, rectangular specifically. How do I select and define the numerous custom angles to show numerous curves on the same plot?
I guess I'm not quite understanding. Let me just read through that myself here. I'm not quite sure I understand the question there. How do I select, define numerous custom angles to show numerous? Okay. Oh, I know. I think I know. You can, again, we'll go back here to TracePro. You can change the number of horizontal angles here at 10. Right now it's set to 1. If I set this to 4, we're now seeing, this isn't a very exciting one to show because it's showing it's a symmetrical, radially symmetric source, but you can enter as many of these as you want here. And you see it adds them over here in the column. So if we set 18, we get every 10 degrees. And it looks like there was a follow-up to the first question on the resolution along the bottom of the graph. And that's really pretty much set. Actually, sorry, you can change that on the rectangular distribution here. The default setting is 90. If you wanted to look at just 45 here, it now changes the bottom scale. So it changes the x-axis, is controlled here with angular width. Okay.
We have a request to discuss or perhaps review your stray light portion of your
okay.
presentation again.
What I did, I'll go back to the presentation here. I was looking at this graph here, or at this irradiance map, and I wanted to see where these rays are coming from, where this light is coming from. So my main area of interest here is this central portion. So I'm considering this straight light. It's not light that I want. So to do this, I selected this area, and I wanted TracePro to tell me where that light was coming from. And the way to do that is, let's see if we can do that live. If I open an irradiance map, this model, I'd already pre-traced these rays, so I don't have as many rays traced in this model as in the example on the webinar. But to select this, say I want to look at this area here in this upper left-hand corner. Just do a shift and left click. Make sure I'm actually in my irradiance map. So shift and left click, and you drag a box to highlight this area. And then you can go to Analysis and Display Selected Rays. And if we go back to our model here, we can see it's only showing me the rays that are hitting this upper left-hand corner of the target. And then we could go back in here to the model, and you could start to zoom in. and see where those rays are coming from. So it's a troubleshooting tool or an analysis tool to let you break down the irradiance map and see just the area you're interested in. Okay, we have some more questions, I think.
We do indeed.
Okay.
Let's see. How difficult is it to change the LED source so that one LED is failed, and then look at the changes to the Candela plots?
Pretty easy, actually. We could go in, if we looked at this here, I'm going to zoom out so I can see the whole thing, and I'm going to turn I want to turn all my rays on. So we could go here to the source menu in TracePro, open up the sources, and I had 7 LEDs, and let me take out one of these LEDs, say LED 3, rerun the ray trace. And while that's running, it's going to take about a half a minute. Let's answer another question, then we'll come back to that one.
Sure.
Yep.
Looks like we have another Candela plot question. Can you specify the different angles for the plots and not just the number of plots? For example, 4 plots gives me 0, 45, 90, and 135. But if I want 0, 10, 20, 30, for instance.
You're going to have to define it just by the number of slices. You can't individually define the angles that you want. So if you wanted every 10 degrees, you'd have to define 18 points, and that would give you every 10 degrees. So no, you can't. Unfortunately, you cannot specifically enter in the values you want. Okay, if we go back to this one here, I just failed one of those LEDs. We don't see much change here. And then if we go to a Candela plot, really don't see any change in Candela. And that's, in this case, what we'd see, actually, if we looked at it, is the difference in total flux. I believe my previous example was about 960 lumens, and now we're at about 840. So we can see total flux differences. But because of the design of this lens array here, we're not really going to see any difference in the patterns because each lenslet is actually overlaying. They're superimposed on the target. So one of them dropping out will change the total flux, but it won't necessarily change the distribution in this case. Okay. It looks like we'd skipped a question here on how does smoothing work.
I was just about to go there.
Okay, sorry about that. Smoothing, what I would say is the formula for smoothing is actually in the TracePro user's manual. So what it does is it applies a formula to smooth the data from one pixel to the next. So if you want to see the exact formula, take a look at the Irradiance map information in the TracePro user manual. And that's up help and then TracePro user manual. You'll be able to find the exact formula for that.
Okay. Next question was, your aspheric lens generated, was it using any particular lens insert function in TracePro?
The lens that I used in the demo here, in this case, was actually a simple spherical lens. So I just had a radius of curvature defined, and I used the insert lens option in TracePro. It's actually being done in this case in the macro, insert lens element, material, position, radius of curvature, and thickness. But you could do that. You could also use the insert lens, and then there's an aspheric section on the insert lens dialog box in TracePro for doing aspheric terms.
Okay. We have a question relative to the luminance and radiance map function.
Okay.
Someone thinks that they haven't been able to make it work, and they think they performed all the necessary parameters have been input. Maybe there's something that's key that they might be forgetting. I don't know.
One of the more common problems with using the radiance and luminance map is, let me go back to this, is your source. If your source is defined as being collimated or normal to the surface, it's very difficult, or if the source is very small, it can be very difficult to get a ray back from your eye position through the target to the source. So luminance and radiance ray trace sources work best with large, wide angular distribution sources. So that may be part of the problem. If you were doing an LED and defining all the light as being normal to the surface, the chance of any ray coming back through this system and being perfectly normal to that surface is infinitesimally small. So you'd have to trace an extremely large number of rays. I would say too, if they're having a problem, send in an example or send in a question to tech support. That's support@lambdares.com, and you can try and troubleshoot it that way.
That sounds like a great idea.
Okay.
Looks like we have a feature request for individually defined angles for the Candela plots.
Okay.
So we could certainly write that down.
I will put that feature request in today.
And then we have a question regarding applying a filter on the source and then checking the real color, or the true color.
You could do that, yes. What you would do is, say we had this, say this example here, we could tint this front lens. We could apply a surface property that has color-dependent transmission. So we're actually defining a filter for that lens, and you could run that ray trace, and then you could look at true color or CIE coordinates for that and see the effects of applying that filter. So I'd apply the filter as a surface property to the lens.
Okay. Let's see. Another question. Why is the total incident flux different when presented in the illuminance map versus the CIE color map on the same surface?
Let me take a look if that was, well, I mean, I'd have to see an example of a model with that to see. They could be, there shouldn't really be a difference, but it could be down to smoothing. Sometimes it comes down to smoothing in different settings. That's why smoothing can give you some erroneous results at times. It can skew the results. So again, if there's a specific example where you're seeing that, please feel free to send that into support, and we can take a look at that.
Okay. Looks like we have a question again regarding Candela plots. Can you basically create a delta plot that compares the differences between two individual Candela plots to see better how they are different?
Yeah, not between Candela plots, but between Irradiance maps you can. So if you were looking at, go back to TracePro, if you're looking at the Irradiance maps, I mentioned earlier the way to get two Irradiance maps on the screen is Tools, Irradiance Viewer. Well, once you bring in an Irradiance map this way, you also have the option of adding or subtracting other Irradiance maps for that. So if you're looking at spatial distribution, yes, you can do that. That feature isn't there right now for the Candela plots, though. But you could export the data from a Candela plot as a text file and do that in, say, Excel and look at it that way. Okay.
Okay. Next question. Why do rays sometimes come out backwards from some of my LED sources when I build them and run the traces? And can I use reverse rays to reverse those rays?
What the chances are, what you're probably seeing coming out backwards could be dependent on any surfaces or Fresnel reflections from surfaces. I really would probably have to see an example to see what's happening specifically. So reverse rays actually works with, it's a reverse ray trace. So that would be tracing back from a target, so probably not what you want to do. Oh, so it comes out of the wrong side of the LED. I'd be looking at which surface of the LED dye you've applied the surface source property to. The rays should be coming out, coming out on the outside of the surface. Sometimes a problem can happen if you embedded your source inside of an object, such as an epoxy. What I'd be looking at then, again, it's still to apply to the top of the die. If you could send us an example, it'd probably be the best way there. But the other thing that can happen is sometimes if your source is embedded in another object, the rays can do some strange things. And the way around that, so say you were trying to model an LED die encapsulated in epoxy. What you can do is go to ray trace options, and just click detect rays starting in bodies. So that could be the issue there.
Okay.
Again, that's under ray trace options, and just select detect rays starting in bodies. I think
Seems we have run out of questions, David.
Okay. Well, we'll throw it open here. Any last questions? If not, as I mentioned, we'll be archiving this webinar, so probably within the next day or so it'll be available for download from the webinar section of our website. And that is at, let me go back to my last screen here. Oh, there we go. So it's at lambdares.com, and then it's in the webinar section. So I don't see any new questions. So I guess for me, that will wrap it up here. Any last words, Andy?
No, I just want to thank everybody again for attending. I hope you learned something, and I hope to see you back the next time we do a webinar.
Okay.
Have a great day, everybody.
Okay. And for me as well, thanks everybody for attending. We'll be doing our next webinar probably in about a month from now, so hopefully we'll see everybody then again. Have a good day.